So,
Yeah.
I'm going to leave the attendance on for a while in case people come a little later.
Okay,
But then
we
at some
don't
point
need
of time we'll shift on to other things.
No.
This is okay. A couple of things, of course. One is so now that we are in the second week or whatever, I think 1.5 weeks are over. I try actually to put names to faces. It's 150 people. It's hard, and it's like extremely hard to hold grudges if you don't have names to faces. So when you have a question, I mean seriously, when you have a question, please state your name. That's one way we'll find out. And there are other ways I'll try to get names to faces. But my hope is, if not all 150, I should get a good set of people whose faces I'll remember. Okay, and good faces to name correspondence I'll remember. Otherwise, it's just an online class. That's not fun. Okay, so when you ask a question, state your name. Okay, and then ask the question. And then if you're asking too many questions, then maybe after the 100th one, you don't have to state the name. I will just tell you, don't ask. It's your name. Okay, the other thing is, please note that the wall clock is 4 minutes faster. Okay, I just established this. There are huge number of cell phone clocks and the computer clocks. According to that, it's 4 minutes faster. So I will keep track of the time, so don't get carried away by that. And it's like huge number of people getting up kills the flow. As to why there should be a flow in the last 4 minutes, that's the climax of the class. There should be flow. Okay, so that's that. And I asked people to sort of give me a sense of whether or not the pace that we tried in the last class, which is the first time we tried to do more technical material, was too slow, too fast, and that was the results. I just kept it open for 1 day. So it's not really 114 hours. I kept it open for 24 hours. And that's about the results. So 15 people thought that they actually read the paper, the book, and then they pretty much understood everything before already. So for them, it was sort of too much of a repetition. 50%, and 25% thought, and 38% thought that they actually got more from the lecture than reading the chapter. They may not have read the chapter. They just like my voice, I don't know. And then finally, another 38% said they did get something out of the class, but really we could have gone faster. So I will try to be faster. And then we'll see how that goes. Okay. So I'm assuming, I'm going to sort of make the assumption that you read, that you did the two things that you're supposed to have done. One is to have looked at the lecture on intelligent agent architectures that I'm more or less going to assume that you have read, and then I'm just going to quickly go through the slides. If there are any questions, you can ask me. Then I will assume that you read the blind search chapter. It's one of those things where normally if I ask you to read the chapter, I don't assume that I don't have to cover it anymore, because after all, the first time you read, you may not understand everything. But blind search possibly is one of those areas which you probably know, because you have done different kinds of blind search algorithms, the depth first, breadth first. Definitely in your 310. We will actually take a fresh look at them very quickly, as you probably saw from the textbook, or if you saw the lecture again for that particular part. And then there was one interesting idea that we had, which you probably never heard of, which is iterative deepening depth first search, which is a cute little idea. And that sort of also explains to you one of the important points, which is you're assuming huge trees. You're assuming huge trees so much so that you go quite deep. And if you're going deep, then essentially, you know this from your old 310, that in a binary tree, for example, there are as many nodes in the last level as there are all the other levels combined. You know this, right? And that's also true for, that's even more true for higher branching factor trees. There are b power d nodes and the depth depth d. And everything else sort of just about comes to b power d. Okay? So that's why, in fact, iterative deepening depth first search works. in certain cases. And I hope you also got the idea, which we'll again double check, that the reason we love depth first search is it takes linear memory. And in fact, one big issue tends to be you may have infinite patience, but you don't have infinite space on your computer. And if your computer actually requires 1 byte more than its total physical and the secondary memory, it just dies if it isn't there. So there'll be a seg for it. So in some sense, we do want to try and look at search algorithms that have lower space complexity in addition to the time complexity. And then hopefully we'll start moving towards cost sensitive and informed search by the end of today's class, and that would be the main point of next class, essentially, which is A-star search. Okay, so in terms of the architectures for agents, you must have looked at these simple reflex agents with state, and goal-based agents, and utility-based agents. And these simple reflex agents, basically, in essence, it's taking what's true, some information from the environment, and it's sort of, here you wrote condition action rules, but it can be some arbitrary function. These rules don't have to be rules, they can be some arbitrary functions. Okay, a reflex agent essentially takes the state and decides what action to do next. And one interesting thing that may not have come through in the textbook is the following. Actually, a lot of the AlphaGo style architectures are reflex agents. Strangely enough, okay? Because what they do is they essentially compile the state of the world as well as their goal as well as what the opponent has done up until now, and they say, if the state of the world is this, and the opponent has done this, and I have done the following thing until now, then the next action I should do is this. That's reflex agent. Okay, so even though in this chapter we try to make fun of reflex agents, sometimes you can compile things into a reflex agent. Okay, so that's useful to keep in mind. And then if the reflex agent actually keeps track of state, in fact, when I was talking about AlphaGo, really it was reflex agent plus a little bit of state at least, because it's keeping track of where it currently is. I was just assuming that the state may have been put into the condition. If you do that, then it will be a reflex agent with respect to the state. But normally, this is a more useful view that the agent requires information about the state. It requires some information about how the world evolves. This is the kind of place where if the world actually is static, the world doesn't evolve. So wherever it is, it just stays there. Okay, if it's a dynamic world, then when you are not looking, the world is changing. The state of the world is changing. So that information has to be put there. And then what do my actions do? Which is basically what we looked at last time. If I do this action, this is how the state of the environment will change. Okay? And then of course, using this, so this is basically reflex agents with state. I would say this is basically connected to AlphaGo style things. Okay? This one essentially, the goal here, in some sense, there's no goal here because the other one, the goal-based agent, has a goal as input. Okay? Here's a funny thing. If you take something as an input, that means you're flexible with respect to that. Do you understand what I'm saying? So this guy will never ask, what's your goal? Because the goal has been built into the condition action rules. There's only a particular goal that you would possibly be doing if you are playing AlphaGo. You just want to win the game. I mean, if you're playing Go, you just want to win the game. If you're playing chess, you want to win the game. And the rules of the chess and Go have already been decided. And so I don't need to tell you every time, hey, go win the game. So you can just kind of compile that in. When you compile that in, there is no separate goal here. Okay? But in general, we don't know what our goal should be when we wake up in the morning. An intelligent agent basically has to also figure out what its goals are and how to make progress towards it. So in one way of looking at this set of these architectures is to say that they're increasing the flexibility of the agent. It can take new problems and still do well. And remember what I said in the very beginning of the class, that computers are already better than you in any given domain. The only thing that you have going for you is the flexibility. Do you see what I'm saying? So in some sense, essentially, that's what you do when you go forward. So if you happen to know what your goal is, then you can just build it in. You can compile it into the architecture. And that's it. You don't need to think at the time of, one of the advantages of compiling it in is at the time of decision, you don't need to think anymore. Right? You just look up the table. There's a huge big table into which it will say, whether it's a table or some function, in AlphaGo kind of a thing, it's a huge function. That's what the neural network underlying is actually implementing. And this function tells you this, and true. This is the action you should be doing. Do you see what I'm saying? Okay? So it looks as if the humans normally may have some things that they can do reflexively, but many things they think. By the way, this is also connected at the start repeating to system 1 and system 2. Remember I talked about system 1 and system 2 last time, the Kahneman-Tversky stuff. System 1, basically, this is like what Kahneman and Tversky said, that we have a system 1 which just makes reflexive decisions. As soon as you walked in, I look at you and say, this guy is sharp. Yeah, maybe he's not sharp. Okay, you come up with these very quick decisions. And then system 2 is the one that sort of slowly deliberates to see if in fact your impulses were actually right. And human evolution depended on both. Like I said, every time you see a tiger, if you hang around and try to figure out whether or not this tiger is from a good family and maybe won't bite you or something, you'll be dead. So you have to have both the reflex as well as the deliberation. As we are going into these architectures, the later architectures allow for upfront deliberation. But then whenever I provide upfront deliberation, then you can also compile it. After, in fact, for example, if I just told you if you just solved yourself a particular search problem, you can remember for this I and this G, this is the answer. So if I give the exact same problem again, you don't have to start from scratch. So second time around, you became reflexive. But the first time around, you actually reasoned from first principles. And human civilization always went that way. Every time, for example, the first time you heard about derivatives, at least the first time mathematicians heard about derivatives, they thought of it as a limit, h tending to 0, fx plus h minus fx by h. When was the last time you actually tried to compute a derivative that way? You essentially said, oh, dxn n by dx is nx power n minus 1. This is a little shortcut. So if you ever see x power n, spit out the answer. If you ever see sin x, spit out the answer. If you ever see log x, spit out the answer. What is the log x derivative, by the way? It's very important in this class. Okay? So you have to spit out these answers, but if I give you some random function, you should know how to go back to the first principles. You see what I'm saying? That's what the flexibility is. Otherwise, you're just basically a lookup table. If you make your own lookup table, you're intelligent. If you're dependent on somebody else's lookup table, you are not intelligent enough because you don't know how to solve the problem. Okay? So that's about reflexive essential states. So already you do a whole bunch. Here you keep all this information and then you use this. And so in some sense, this really is almost close to what AlphaGo does. This is the kind of architecture they have. You see what I'm saying? Much of this may well be compiled into this big function, but essentially that's what the information they need. Yes, go ahead. Name?
My name is Yash.
Okay.
So, how is the state? Does the state have inputs? Does the state have involved in the actions? Do they have input?
No, basically it's all coming from the sensors.
Yeah. But, so your errors are all drawing to what is the goal plan?
No, so basically, yes, it's true. So that's a good point. So in essence, the agent is remembering. I'm not putting agents the way agent updated its state, but it's basically being updated by the sensor information. That's a good point. Okay, so this is something that I spent a bunch of time actually, like let me get back to this after the next one. Oh, why did I? Okay, wait, there is a problem here. Yeah, okay, let me do this first. So then there is a goal-based agent. And the difference between the goal-based agent and the reflex agent with state is very little. It's just that you take as input goals. By the way, again, please understand, if you take as input additional parameters of the problem, you're being more flexible. Right? If you ever come to the exam and say, don't give me the paper, I know the answers already. That means you just assumed, you sort of saw some, fake exam paper somewhere and you just assumed that that would be the same exam paper. And you started writing those answers. Do you see what I'm saying? Okay. So in fact, taking goals as input shows that you're more flexible. You can deal with multiple different kinds of goals. At least you're allowing that possibility. And then you're taking the state and how the world evolves. Now when this is there, one of the interesting questions, actually it's true also in the previous one, is when you have state information, the kinds of reasoning that the agent does involves, for example, how did the state evolve? What is the current state? Now you think you should know the current state because the sensor information is coming in. But that's not true because your sensors might be limited. You only get partial information. Right? So for example, just to put this in perspective, if you're driving, at some point of time you pass this guy on the right-hand side, right-hand side of you, the lane to the right of you. And after a while you look back, there's no car in the rear view mirror. Is the car still there or not? It could be in the blind spot. If you just saw a few seconds after you passed the car, you are not seeing the car in the rear view mirror because it went into your blind spot. At that point, just assuming, since I don't see a car, it's all completely fine, carless right lane, now let me get into the right lane, would cause lots of problems. So you actually update your state. Yes, the sensors are saying there's no car, but 3 seconds back, the sensors told me there was a car, and I know how the world evolves. There are no atomic cars which just zoom past, and so there actually must be a car still in the right lane which just is stuck in my blind spot. This is the reasoning you do. Okay? And then so you have a sense of what the current world is, and then you ask yourself, what should I do? If I were to do an action, what the world would look like? This is simulating. Much of what is happening here is simulating in the head. If you simulate the world in your head, you never get injured. Do you see what I'm saying? If you actually try to do an action in the real world, you might go under a truck. If you think of doing this action in your head, you don't die. So in fact, a lot of intelligence is ability to simulate the real world in your little head. That's how we have actually survived. We are able to, sometimes you have to do stuff in the world to figure out what happens, but many a time you avoid doing stuff. You can think about what will happen if I do this. Because you have knowledge about the world, you have models of the world, so you can essentially simulate the world in your head. Okay? So then, if you have that information, then I know the goals. If I have this information and I know the goals, then I should ask what should the action be that I should do next. And you can almost see that in the problem-solving agent which you looked at for the search algorithms. Essentially, this stuff is the child generator function. Okay? And the goal is a goal test function. And this stuff is the search algorithm. What action should I do now is a search algorithm. There are many different ways of instantiating this, but the first one is making them all procedural. Just make them pieces of code. And even if you do that, you can essentially do reasoning in the world. I mean, you can behave in the world because you can do search algorithms. Okay? And now I want to actually go back and point out that what I said here is this is an orthogonal issue from the architectures of the agents that you want to keep in mind, which is that the simplest agents assume the states are atomic. That means they are black boxes. They are indivisible black boxes. Problem-solving agent at the program level essentially doesn't even know what its state is. What it knows is there is a state black box, and then it gives it to the child generator. It gives more state black boxes, and then it gives each of them to the goal test engine, goal test code, and the goal test says, yes, it's a goal, you stop. Otherwise, you keep on doing this. That's what you found. And the difference between all the search algorithms turns out to be the order in which you take the next child, next node to expand. Expand essentially means apply the child generator function to that state. So at the problem-solving agent level, we think in terms of atomic agents. State spaces are indivisible. There is no internal structure you are assuming. Okay? And then the focus will be in search on atomic states. And in fact, if you think of A-star search and the next idea that we will look at in this class, which is Markov decision processes, they both will be first presented at the atomic level. It's always done that way. And then you say the states have structure. If the states have structure, then for example, here is one way of looking at it. The states might actually be made of features. And if they are binary or Boolean features, then essentially you call that a propositionally represented state. Now, if a state has n state variables and they're all Boolean, so they can all be independently true or false, which means with these n state variables, you can represent 2 power n different states. What did you do just now? What you did is the propositional representation allows for compactness of the representation. Do you see what I'm saying? You can remember the world which is 2 power n states large in just n bits, where n bits are the Boolean state variables. So that's propositional. We will then also talk about, at the level of propositional representations, essentially, from a machine learning-ish perspective, and unfortunately, many of you have kind of heard about that stuff, you can think of propositional as features. Except a feature really doesn't have to be, I don't know, it doesn't want to come. Okay, a feature can be multi-valued. In fact, normal machine learning-ish stuff says a feature can be continuous valued, a multi-valued discrete variable, or Boolean discrete variable. Okay, so here we'll think of, at this level, think in terms of propositional. That means they are discrete Boolean variables. That's the first entry for us. Okay, so the states are made of state variables that take values, and the propositional multi-valued are continuous, and then what you can then do is you can do search as well as inference on the states, which we will understand when we get to something like propositional logic. If the following state variable is true, would this other variable also be true? Because they have connections, they have dependencies between the variables. Okay? And then there is relational representations. Up until here, essentially, from a logical semantics perspective, what you will think is that essentially the world is made up of true-false statements. Okay? So in some sense, going from here, you think the world is made up of indivisible states. Here you think the world is made up of true-false statements. Here, you come to relational, you think the world is made up of objects and the relations between them. And then when you come here, relational to first order is actually similar. It also can allow functions over objects. And a strange way of thinking about this is the way you learn programming languages. from assembly language to any higher level programming language, especially things like object-oriented programming languages, essentially assume that the program is talking about states of different objects. So you make what is this thing called ontological commitment. Ontological commitment that my world contains objects and relations between them. Okay? And then you try to look for a language that will allow you to represent that. That's where your logics come. Okay? And the other thing, of course, so this is an example that you should go through, hopefully you went through carefully, that it's the same problem can be represented either in atomic or in relational representations. And one funny thing that actually problem-solving agents do is, on one hand, I'd like to introduce problem-solving agents as if they're only doing search in the space of atomic states. But oftentimes, they actually say that states are made up of state variables. This is what I'm saying. Some of the examples we'll look at, you'll see that sometimes states are made up of just indivisible representations, sometimes states are made up of state variables. You know, for example, for the 8 puzzle problem that you probably looked at, that you must have looked at when you looked at the search algorithms, then you basically talked about where the blank is and where each of the tiles are in the puzzle. The difference basically is that the search algorithm within its innards doesn't do any inference on the state. It doesn't, for example, say, if this state variable is true, this state variable is true, will this other variable be true? It won't ask those kinds of questions. It was just a representational convenience that you might do. Okay, yes?
In the video example, you talked about the dirt and the Roomba, where you can reverse their binary states. So you have the Roomba in true, false, and then dirt left, right room. And that
No, but these are all Boolean variables anyway.
right. But if you switch the Roomba to be left, right, and then the dirt to be, true, false, and then the dirt to be left, right, you're imposing states that are there, but they can't exist. So
that's a very good point, actually. In general, let me say two things. One is, I haven't seen my lecture. I gave it in 2012. So I'm trying to figure out what I might have said in 2012 while listening to you. But secondly, I think I know where you're going, which is, if I give you state variables, in the worst case, if there are n Boolean state variables, in the worst case, there will be 2 power n states. It doesn't have to be. Some of those states might actually exist, but the agent can never get to them. Do you understand what I'm saying? So this is the kind of thing you're talking about. So for example, this actually causes all sorts of interesting questions about what are good versus bad representations. Okay, so one of the things that might happen is, I don't know if I will get to this, in the 8 puzzle problem, actually let me see if I can get to that very quickly and come back. Oh my God. Yeah, this guy. 8 puzzle problem, as boring as it is and as painful as it is for you guys, because you have to do it in terms of search algorithms, actually it played a huge role in the culture. Back when, apparently this guy called, instead of 8, it would be 15 puzzle. So 8 would be 3 by 3 with a blank. 15 will be 4 by 4 with a blank. You see? Okay? And then, so Sam Lloyd essentially gave this puzzle. This is an 8 puzzle problem. Okay? And said solve it. That means just move the blanks around until you get essentially everything in the right order. So here, of course, 14 and 15 are in the reverse order. Just put it right here. Looks nice, right? It's an easy enough problem. And this guy is going crazy because it turns out, given the legal moves of 8 puzzle, given the legal moves of 8 puzzle, its state space is split into 2 disconnected components. This is almost like this sort of Inception, Interstellar kind of stuff, different worlds, okay? Given the moves of the 8 puzzle problem, the state space is split into 2 disconnected components. And if you are in one component, doing operations will only keep you in that component. You will never be able to get to the other component. The easiest way of getting to the other component, into the tesseract, so to say, would be take 2 tiles, swap them physically. You see what I'm saying? That's what Sam Lloyd did. So those were the days when learning combinatorics a little ahead of the rest of the bozos got you a lot of fame. You see what I'm saying? So this gives you an answer to some extent that, in fact, you might then argue, why can't I somehow come up with a representation which only corresponds to one, only allows legal operations such that as soon as you give me this as the initial state, you'll say the problem cannot be solved. Unsolvability of problems is a problem in itself. If I give you a problem and you have to say it is unsolvable, the way to do it is actually exhaustively search and find that there is no way of doing it. You can't just look at it and say, I'm feeling bored, I think it can't be solved. You see what I'm saying? That's actually a deep question, essentially. In general, for any representation you can come up with, an arbitrary assignment of feature values might correspond to states that are physically impossible. What I mean physically impossible is that the legal operations, there is no sequence of legal operations starting from initial state can never get you to the goal state. Okay? Actually, this is the problem. Everything that we are talking about has layers and layers of complexity. So if you ask questions, that's the way I can get into that. You can slow me down. I will try to go fast if it's possible for me, but you can slow me down by asking questions. That's your way. By the way, what's your name?
Ian.
What?
Ian.
Here, okay. Yeah, remember, people say the names. Okay. So anyway, this is the stuff that I said, that the text, the course is essentially looking into the representations because you want to know how to represent these things. You want to look at how to search. So there are the search algorithms, MDPs, and A-star search, etc. come here. And then there is this other elephant in the room, which is learning or acquiring the model. So I would not say learning, I would just say who gave me the model. And that's what actually got me to this slide that I hope you understood, that there are 2 ways of going about intelligent agent design. One is assume that the models are given. Model of what will happen if I do this action is given, model of how the world evolves is given, and you kind of are given a representation for the state, what are the relevant state variables to think in terms of. Okay? If I do